So we all suck on the homework.
I understood like what you all were doing with the finite operator, but whenever you have the infinitesimal like dA squared, it goes to 0.
0, yeah.
But whenever you have just a squared, it wouldn't go to 0.
Yeah.
So that's why I was like, how do you get from the infinite to the finite step?
Oh.
I thought we were just dropping the a squared term and doing an approximation. Since
Yeah.
it's going to be small squaring, it's going to go
If it's infinitesimal, that makes sense.
right.
Yeah. So for this case, remember last time, last semester, they also have a spin, and the spin inner product is the normal or in something like this. You have put here, then you have
Still
R,
write them
which is
separately.
Rx, Y, R. Okay, let me just. Okay, keep continuing here. This is X components, right? Y components.
Yeah.
Here components with AX, PX, and plus AY, PY,
Right.
plus AZ, PZ. Then you just see each. I think this one is just, if you consider less translation to this operator, but this commute with this one, right? Because this.
So it's 0.
Yeah, this one with this one commute, not commute, right? It's AX bar, right? And but this commute all that others, and then you need to each individual. So you have something like A, B, and then
So-
yeah, each one. Then you find you have something this one with.
So A in this question is just a normal vector. It's not an operator.
The operator is a position operator.
Okay.
Yeah, so that is X position. Then if a position operator is AI, it's like A,
It still has the
it's
unit vector.
something numbers with unit, okay, whatever. Something like this, right?
Yeah.
And then the A, okay, no. Just say AX, AY, AZ.
Yeah.
Yeah, and that is scalar.
Okay.
So then you can, each are scalar and each individual you can find this commutator relation. Then you will find, so in the exponential you have, if you have a first one, the second one you found that you have a, so, oh, I didn't give you the hint.
You
Oh
said
yeah, I
to
gave you
look
the
at
equation, but didn't write down here, right? Yeah, that equation, that I think in your case, right? So you have equation 217. Yeah, so you have, this is the exponential A, and operator B, exponential A minus A. So this one is your U, right? Sorry, which one? Which one is your U? 7.3.
Yeah, U is
E to the power of minus I over H bar.
So
A
this is
dot
a U.
P.
This is a U?
U is
E to the power of.
where A is the I over H bar.
Okay. So, okay, so the B in this case R, right?
Yeah.
Okay. So then this case A is this one without P, right? And also you have I over H bar.
Right.
Yes. So then this was equal to the formula here equal to B first is R plus A, okay, plus, of course you have also, do not remember, use this one, right? Yeah, so this is R. And second one is A, B, I, or H bar is R. So if you know this, let's do this one first. You will see some numbers, I think, right? Some numbers with coefficient. So something like, and then if this number is a constant, all others 0. So then here, this one actually give you A. Because you have a component, right? X with this is vector. That makes sense?
Yeah.
Okay, if you have not do this, use a finite, not use infinitesimal. You can turn on the Wednesday. Okay, this is yours.
That's mine.
You want to do more?
Yeah.
Okay.
I'm getting an image.
All right, that's yeah, infinitesimal is easier, but I think I just want to play. You're familiar with this, and actually this is a very useful equation or relation. So, all right, now let's continue discuss.
Can I ask you one more
Yeah,
question about
yeah,
homework?
yeah.
If we were to use the recursion relation to get the expectation value of R,
Mm-hmm.
and there's say 2 different values of n in the wave function, would we just like take the sum over this, or would this be like an improper way to do it, like the expectation value of 1, 0 plus the expectation value of 2, 1?
Wait a moment. Which question? It's 16, right?
Yeah, 6.
It's asking you n, right? It's oh, okay. 16 is a combination of this wave function. Is that correct?
Yes.
Okay.
And that's
in
what I
that
was-
case, you need sum of yes.
I wasn't sure if you could use the recursion relation really or not.
Yeah, if you for each one you can use, right? Is that correct? What's your question?
Yeah, I'm
Recursion means
saying
like
that
this. Yeah,
makes
yeah.
sense.
You just use.
Okay.
Yeah. That's I found some of the do the details. That takes time, but you just direct use those. That I just want to use practice how to apply that.
Okay.
Okay. Yeah. All right. Any other question? Your question already. Okay. All right. Keep continue. We have addition of angular momentum. And we already worked on try to double check it is angular momentum. And follow this intervector. It is also commutative relation. Follow this the angular momentum. And then we also found this how to express this in terms of the J1, J2, or J1 squared. Any rest all others. But now we already down to here. We know J squared, Jz. J1 square, J2 square. This commute, right? So this makes a group with the commute. Just remind you. Mutually commute. So we have this space. We're going to use J1, J2, Jn. Is J1 eigenspace for this. That is group 1. Group 2, we have also J1 square, J2 square, J1z, J2z. We also mutually commute. Right, so then we also have a joint eigenspace J1, J2, J1. So now we first, we already answered the first question. We already answered the 3. Now we go to the, try to finish the number 4 and number 5. The eigenvalues of G squared and Gz. This is question 4. And then I'm going to eigenstates of this. We're going to find this. So now let's continue this one. Remember, we know, okay, that's still we have, this is a J1, this is J2, so we have, this gives us J minimum, right? And then arbitrary case, J1, J2, so this gives us the total J here. And this is giving alpha. So this value is be larger than this one, and the maximum is J1, J2, and this gave us J maximum. So we know for giving J1, J2, depending on the angle between this J1, J2, the orientation, we can have a maximum value of the additional total J, or some value smaller than the maximum but smaller than maximum but larger than minimum, right? Okay, so now we have the allowed J value must be within this one, right? By analysis. And this one, the value for this depends on the angle between J1 and J2, right? So now, we know for given J1, J2, there's a possible, not only one J value, it is a group. And that means it's between these two maximum value and the minimum value. So now we are going to find what is maximum, what is minimum. Once we know these two, so we can determine, oh, once give me the J1, J2, I need to know all the allowed J value is within these two. So now next job is we are going to find how to determine J maximum and J minimum. Okay, so now let's work this one, J maximum first, since that is easier. For J maximum, let's look this figure here. So now I use graphic A, Jx and Jy, and this is a Jz. So now we have, suppose J1 is here, and J2 is here. That is for giving alpha, right? So this is alpha angle here. Then we know the J, addition of these two, this J is here, right? Okay. So if J is here, now what is the, suppose J is here, so we know this value is this one, right? H bar multiplied the square root J multiplied J plus 1. But we do not know J, right? So now this is what we are going to find. Now, for this one, let's look this. Suppose the project to here, this should be M H bar, right? This is the Z components of J. So we know because M, for giving J, right? M always like this because it's angular momentum. Since we already proved, so all the followed angular momentum properties, chapter 5 we already discussed. For giving J, M values be between positive J and negative J. So what is M value? It is J project along the Z direction. So that is this value. Now let's look at this relation between M and M1, M2. Now here, this value is M2 H bar, right? This is J2 project to, so this one is J2Z. And the J1Z is here, right? M1 H bar. So what is the relation between M, M1, H2? Since geographically we know this one, this one. This one is M1 H bar. You agree? Because this one is J1, right? So then J1 project to Z direction is this matrix B equal to this one, right? You agree? Okay. Then, did you find the relation between M, M1, M2? This is M. This is M1 H bar. This is M2 H bar. So immediately you have M is always equal to M1 plus M2. This is a very important relation we call selection rule. So whenever you have the orientation between J1, J2 and form this addition angular momentum, but we know the project to Z direction is always simply the addition of two Z components. Is here. Okay. With this relation, now we are going to find this because this helps us. So now consider M max. How much it is? According to this, right? M always between or equal to the J and larger or equal to max J. So that M max equal to J max, right? That is first issue from here. As a single angular momentum M value and J value always have this. Now that is what this one. Second, from here. So from here come to here, M max should be the max value of this should be M1 max plus M2 max, right? The max value of M thus be correspond to the max value of M1 plus max value of M2. If we select J as maximum, this is arbitrary, not maximum, but whatever is maximum is more, but always have this. So if this value is maximum, that is maximum value project to the Z direction, that's in M max, right? And that's be equal to M1 max plus M2 max, right? So that is it. So if these two be equal, right? Okay. Further, what is M1 max? Follow similar relation. As angular momentum will be J1, right? Since the max value of M, we always take J value. For giving M1 max, well, that's be correspond to J1, right? So now, combine it together, we immediately got this one very easily. So, J max value is simply additional J1 plus J2, and that makes sense. If you come back to here, you know the J1 magnitude, J2 magnitude, and the J max must be simply the addition of those two. Of course, I mean here this vector is because take this one, but the quantum number follow this, right? Okay. So if we finish, now we go to this one. How to find this one? Now we are going to use another information. Remember we have these two groups form this space, right? So this group mutually commute each other. We have four operators, and this group have joint eigenstates this. What is dimension this? For all the possible M value from minus J to J maximum, J minimum, sorry. It's be all the possible allowed J from J minimum to J maximum, and for given J is M is 2J plus 1, right? That is the dimension of this. This is here, right? So for given J1, J2, allowed J value is from J minimum to J maximum. And for each given J is 2J plus 1 for M value. So that is, and how much it is we are going to use. And this one, for this dimension we know it's a subspace of J1, J2, right? Each one is 2J1 plus 1 multiplied 2J2 plus 1. So these two subspace be equal, since they just for given two J1, J2, you either use this as basis set or use this one, right? So space dimensions. So because now we are going to use this n equal to, I'm going to write again, J minimum or J maximum, 2J plus 1 should be equal to 2J1 plus 1 multiplied 2J2 plus 1. So we are going to use this. Since we know the maximum, from this equation we can get minimum. That is the equation we can use, or relation. So now we are going to calculate this one. This is a sum. What is arithmetic, right? Simple sum, right? So for this sum, that equal to, let's suppose we have a sum for given n is n from I from 1 to n, ai. In this case, that's equal to n, total number of the how many terms, right? And a1 plus an factor 2, right? That is this formula. So now we are going to use. So I use this one. Then here, the left-hand side is summation j minimum, j maximum, 2j plus 1 equal to how many number of terms? J max minus j minimum plus 1, right? Okay. First term, right? First term, A1 is correspond to this one, 2j minimum plus 1. Last term, 2j maximum plus 1. Okay, and then so this is simply math. So now I'll just give you the result. That's simply, let me give the second last step is j max plus 1 minus j minimum multiply j max plus 1 plus j minimum. You can very easily compare, right? Then that is j max plus 1 square minus j minimum square, right? That is left side, so that's equal to right hand side. That is 2j1 plus 1 multiplied 2j2. And j max, okay. J max we already have, right? j1 plus j2 plus 1 squared minus j2. So this equation only for j minimum. Then by solving this, you are going to find j minimum is okay. Is here. Okay, the minimum square is. I'll just give you final result is j1 minus j2 square. You just do this very easily both sides. So okay, so j minimum. Since j has to be positive value, right? So we only take the absolute value of this difference. That is j minimum. Now we have answered this question for here. So the allowed j value. So now allowed j value is the difference between two value, the individual angular momentum. That is, and that makes sense, since for minimum, that's the difference, right? The reason why we use the absolute value because we just, j values be always positive. So whatever j1, j2, which one small, which one big, it's fine. We just need the difference, right? Okay, so now we answer the question about the eigenvalue. Now we have j, so once we have j, m is this one. So that altogether we have. So answer this question about this one. Eigenvalue for j square is this one. H bar square j multiplied j plus 1. Eigenvalue jz is m. How to determine the j and m for given j1, j2 is found. So next, we're going to answer this question. The last one. how to determine the joint eigenstate of this. Okay, to do this, usually in chapter 2 or even the chapter 4, chapter 6, we show each detail can, oh, that's chapter 5, I'm removing that. Usually we need to solve an eigenvalue problem, right? But now, since we already know the G1, G2, each individual, the solution of the eigenstates, right, for each individual. That is this product. So since this is known, so we are going to use this one or express this one in terms of this. Since this is known, then let's see the coefficient, right? So now let me okay, because J1, J2, M1, M2 is, since each individual G1, G2, we are assuming they are independent in two different subspace. So they are, I can do the direct products of, right? This one is equivalent to this. And this is each individual eigenstates of individual angular momentum. So, okay, for that, and we know this, and also, and because this space, the joint eigenstate form this complete space, right? So we know the completeness is sum of all M1 from minus G1 to G1, and sum of all M2 from minus G2 to G2. This the product, the operator, right? G1, G2, the pad, G2, M1, M2, and draw G1, G2, M1, M2 equal to what? I, right? This is very important. We always use this because this can help us. Can I erase this part? So now we are going to find now G1, G2, Gm. Since G1, G2 always given, right? So from now on we just use Gm. So Gm just means is this joint eigenstate for given G1, G2. Now we are going to find equal to what, right? That is our question. How to obtain this? Now I'm going to insert, because they cat Gm, I'm going to insert I Gm because equal, right? Then I is here. So the goal is that we are going to use some of known information to find a known. So now M1 from minus G1 to G1, M2 from minus G2, okay, G1, G2, M1, M2, G1, G2, M1, M2, Gm. Now this summation for all M1, M2 here. This is in the product, right? So that's the coefficient, and this is some linear combination of all the coefficient respect or expand this one in terms of this, right? So now I'm going to, since you know M1, I just write down M1, you know from where, from minus 1 here, right? So I just simply 2. Now I'm going to introduce this coefficient, because this is a sum scalar product. So G1, G2, G, M1, M2, M. This one we call Flabish coefficient. This will come Flabish. Yes. So now let me ask you here. The summation for M1, M2 is all values or the selection rule. Summing, right? So now this summation does not mean summing all. We always require our M1, M2 always satisfy this. So all the summation you have to judge yourself how much it is. We always all the M1 allow the M value, M2 value, but their additions equal to M. M is given. For any given M and J, we are going to find how to find this expression in terms of this Calabish called this coefficient, but here always. So that is the trick, or something you be careful here. So now we introduce this, and now let's give a definition since I already have just here. Index here is the lower the subscript is magnesium, the quantum number, and the superscript is momentum square argument. So that is the graph, because this space project to this space, right? So that is graph be G1, G2, M1, M2, and Jm project to that. Or the Gm, the components of Gm in this space, right, correspond to this basis vector, if we consider as a basis vector, like just, so that is this one, right, definition. Now, how about this complex conjugate? We can also do the same things, so you can have similarly. If we consider G1, G2, M1, M2, we also insert unity the identity operator I. Now I'm going to use the completeness of this basis. Same thing like this, right? So that is summation for J from J minimum J maximum, summation for M from minus J to J, and then here this is a Jm, right? This is a I, right? And G1, G2, M1. This is the opposite. We use the eigenstates in this second group space project to the first group space. So then now you can see here another coefficient. Then here, if you look that one with this definition, just complex conjugate, right? So that's equal to summation G minimum, G maximum, and J to J. And then this is a C, J1, J2, J, M1, M2, M. Right, because here, this one is nothing but the conjugate, complex conjugate of this Calabish coefficient. Gn, G1, G2, M1, M2 is equal to G1, G2, M1, M2, Gn. Right, same thing. So that means the Calabish-Gordon's coefficient, even if it is complex, it has its own number and it's a complex conjugate. But by convening, we all set the real value. By convention, right? So just follow the convention. All the people say that. Let's just select this. This real part. Real. Okay. To make the simple, CG means C dot G dot means Calabish-Gordon coefficient. Okay, so from now on, all the real value. Okay. So this is how we introduce the CG coefficient. And once we know CG coefficient, we can obtain the eigenstates. So to obtain the eigenstate or express eigenstates, we turn to find this Clebsch-Gordon coefficient. Now, before we know how to calculate, first let's discuss its properties. Since we are going to use those properties when we do the calculation to find this CG coefficient. Properties. First one, it is also normalization. See here, this is for giving G1, G2, G and M1, M2, M, we have 1. Then if we sum over all this G and M value, okay, let's first look at this. For different M1, M2, we sum over all the M1, M2, and then let's look at this combination, G1, G2, and G prime. So we have given G1, G2, there are a lot of value of G, right? And for given G, there's a lot of M. So we are going to sum all the possible G value and M value. C, G1, G2, G, M1, M2, M. So this is summation for all the Clebsch-Gordon coefficient for giving G1, G2, and M1, M2, but different G and M values. So we sum all. Yes, okay. So sum over all the M and so given G1, G2, we have all a lot of value of M1, M2. Then if G1 or if G and M does not prime does not equal to this gives us the orthogonal property that is delta G prime and delta M prime. So if G is not equal to G prime or M not equal to M prime, that's equal to 0. That is orthogonal. And so if G prime equal to G and M equal to M prime, then we know this summation is summation of the square of Clebsch-Gordon coefficient, G1, G2, G, M1, M2, and equal to 1. So that is normalization, right? So that is orthogonal normalization. If they are same, then sum all together 3. So this properties we later are going to use. Another case. This is a likewise. That is a summation for all the M1, M2. Another case, we have the same G and M, but different M1, M2. Then sum all the G and M. G from G minimum, G maximum, M from minus G to G. Then this Clebsch-Gordon coefficient G1, G2 always have G except, but M1 prime, M2 prime, M and G except. It's complex conjugate, and we know that is real, right? So that is C, G1, G2, G, M1, M2, M. So here, this first sum for all the G and M, but different M1 and M2. Then we know if they are different, this is also. And only when M1 prime equal to M1 and M2 prime equal to M2, we have a solution for G, G minimum, G maximum, and G between this square of the Clebsch coefficient between J1, J2, then we have another J, N1, N2, N square equal to 1. So there are two ways. This is in the space of the joint eigenspace J1, J2, J1Z, J2Z. This in the joint eigenstate of J square, Jz, J1 square, Jz square, J2Z, right? So all this, whatever in which space the CT coefficient is also normalized, as the orthogonal or normalized. This is the first property. Second one, which we already discussed, but now we discuss M3 equal to M1 plus M2. How about the Clebsch coefficient? So that is a selection rule of coefficient. Okay. So let's look at this. J1, J2, N1, N2 in with this J Z minus J1Z minus J2Z. Let's do this one. And between these two states, right? Jz equal to J1Z plus J2Z, right? So Jz minus J1Z minus J2Z is equal to 0. So that is equal to J1, J2, N1, N2, 0 operator, Jn. And that's because it's 0, right? That is, we have this. That is only look this operator. Now we are going to look this eigenstates, right? So now J1, J2, N1, N2, Jz minus J1Z minus J2Z. This is eigenstate of Jz, right? Not eigenstate of J1, J1Z, J2Z. But this one is eigenstate of J1Z, J2Z, not this one. So you can apply this to this one, to the right hand side, and apply this to the right hand side. You agree? When you deal with this. So you just look, okay, this is the operator, addition or sum of operator. But if this operator, if the eigenstate is one of the operator, then you just apply here. If yes, it's this one, you just apply here. So then that gives us J1, J2, M1, M2. This apply this is give us M H bar, right? Jz to Jm. And then J1Z to here is minus M1 H bar minus M2 H bar. Yeah. So we have this. And this initially is this one, right? So this one either equal to this, not equal to 0, or equal to this. So equation 1 should be equal to equation 2, right? So that gives us n minus n1 minus n2 multiplied J1, J2, n1, n2, n equal to 0. I take off the h bar because that's a constant. Okay, so if this is equal to 0, then we can discuss. Equal to, okay, first, this one is what? Clebsch-Gordan's coefficient, right? So this Clebsch-Gordan coefficient is equal to 0 if this term not is 0, this must be 0, right? If this term 0, this cannot be not. So not, if this term is 0, that means, okay, not 0, so if m is not equal to m1 plus m2. and not 0 if M1 equal to M1. So next up, when we have, remember if any, here we have a summation M1, M2, and CG1, G2, G M1, M2, M, G1, G2, M1, M2. Here you have several coefficients, right, to take. Then you just select this one. Those other terms 0, you don't need to consider. That is also, as I mentioned here, if you follow this, that is automatically you ignore those parts. That makes sense? So your Cauchy coefficient, you always satisfy M equal to M1 plus M2. So if not, that coefficient should be 0. That is the selection property of this Cauchy coefficient. Okay. Yes, yes.
That second condition, for the does not equal 0, to the right.
This one?
Right.
Here, yeah.
Should that be n equals m1 plus m2?
Oh, sorry.
Yeah.
On that same note, would
Yeah.
it also be possible for it to be equal to 0 or
Might
not
be.
equal?
Yeah, but yeah, that might be, but equal to 0. You see, I think all zeros be satisfied this one. But yeah, so far I have no. This is I'm going to give you the table. Didn't see any 0 coefficient for this case. Okay. All right. So that is the property. Now next question: how to obtain or how to calculate. That is not simple, but we need to learn some of these recursion equations which can help us. And some case, I give you the table, so if in this homework or in this exam, if that within this table, you can use this table, don't need to do calculation. I'm going to let you know how to use that table. But first, okay, how to calculate. First, let's consider two limit case. Two limit case is if G equal to G maximum, then M maximum is G M minimum minus G max, right? So these two limits are very easy. So now let's do that. This G equal to G max and M equal to M max. Let's consider this case first. So this case means, let's do it. So because G M equal to, let's just repeat again. And then we're going to use this solution here. So now CG1, G2, GM1, M2, and G1, G3. M1, M2. Then, for this case, G maximum. Okay. We need immediate uses, right? Since not okay. G maximum and M maximum, right? That's equal to G1 plus G1 and M maximum equal to G1 plus G1, G2 sorry. This state. So let's look, if we want to expand this state, correspond to Cauchy coefficient. So here, summation, M1, M2, but M1 plus M2 is equal to M maximum. In this case, it's G1 plus G2. Right? So here, C G1, G2, G, M1, M2. J1 plus J2, and you need to get the second step. J maximum, M maximum, J1, J2, M1, M2, and that's equal to M1, M2, M1 plus M2 equal to J1 plus J2, C J1, J2, J M1, M2. Now J1 plus J2, right, because it's J maximum. And then M maximum is J1 plus J2, J1, J2, M1, M2. Now, according to this, so M1 plus M2 speed equal to J1 plus J2. What does it mean? M1 speed must take the maximum value. Right, because only when M1 maximum value is equal to J1 and when also M2 value is equal to the J2, then we have M1 plus M2 equal to M max equal to M, which is equal to J1 plus J2. So that means there's no any summation. So here, that means M1 equal to J1 and M2 only have these two. No any other value, right? So for the summation M2, you only have 1 when M2 equal to J2. Then go to the M1, that summation only 1, which is J1. So this summation became only when M1 equal to J1, right? And M2, J2, and M is J1 plus J2. J1, J2, J1.
Why could it not be reversed? So like M1 equals J2, M2 equals J1.
It is important. M1 is what? M1 is the Z component, J1, Z component of J1, right? J1, for given J1, M1, M1 can only be in the space, subspace of J1, right? Cannot be go to the J2. So M1 is only along here, M2 is only between J2 and J2. So you cannot take M1 is J2 and M2, yes, that is not. All right, so now it's only one coefficient here. Now the left-hand side is where it is here, right? So now we can use the normalization of the eigenspace. Since this is only one Lebesgue coefficient, we can easily, okay, we have that. So now because G1 plus G1, G1 plus G1 multiply itself, equal to 1, right? This is a G, this is a M, this is a G, this is a M, right? So that is normalized. So that is this one, right? It is a cat is equal to this, then that means we have Lebesgue coefficient square, because it's real, right? We already assume that this is real. Square equal to G1, G2, G1, G2, right, the left-hand side here. This cat equal to the coefficient multiply this cat, and then we do the inner product. This one is also normalized equal to 1. So we have the Lebesgue coefficient for maximum J maximum value and the M max value. That one is 1 coefficient. So that means for any case, whenever you give in J1, J2, I know the Lebesgue coefficient for max J1, for maximum J and the maximum M, that's equal to 1. Yeah. And now similarly, this is a one limit, up limit, right? And now let's go to the low limit. The limit is the m minus fixed negative G max value, right? So since okay, let me just get the numbers. G still equal to G max. G1 plus G2, but m is equal to m minimum, right? So m equal to minus G max equal to minus G1 plus G2. That's another case. So this because we know the m value, which is G equal to G, right? And now this is negative G so because m G max G max which is negative G1. So we select these two limits. One is correspond to the maximum value of m, and now it's negative value of G max. For this one, we already obtained one. Now we are going to consider this case. So that is one case. So now let's look. Okay, again we use this formula here. So now I immediately got this J1 plus J2, right? That's G max, this one. Then now m is negative G1 plus G2. That is this space. And we are going to make the summation. So now let's still go to the intermediate step. M1, M2, but M1 plus M2 equal to negative G1 plus G2. According to select group, right? And C G1, G2, G M1, G1, G is just here, right? G is G1 plus G2. M negative G1 plus G2. Now we are going to use this. Since if m1 plus m2 equal to negative G1, G2, only when here, right? M take the negative for G1, m1 and m2 take negative. So that is only when there are two. This requires m1 equal to negative G1 and m2 equal to negative G2. That is select rule. So this summation became only one term, which is minus G1 minus G2 and minus G1 plus G2. Similarly, you can use this normalization of this this. One, right? Another is equal to this square of this very strong coefficient minus G1 minus G2 minus G1 plus G2 square equal to G1 G2 minus G1 minus G2. So we have another limit which is also give the coefficient to be equal to 1. These two limits, so when you deal with this, if you have these two limits, you just immediately know that is in the space here. So now we have J1, J2, J1 plus J2, minus J1, minus J2, minus J1 plus J2. Two limits. The others is not easy. We need the recursion equation. Now let's derive. Set 3, right? We're going to derive this recursion relation first. Let's consider this case. First, consider this one. G1, G2, M1, M2. The G plus minus sandwich between these two states. So now let's look at this, and then we are going to find some part of the relation of the gradical relation. Right? So now, let's do. Let's consider apply to the right to these states. Because this can either apply here or apply here, right? So now let's do first apply this eigenstate of this. Because it's G plus minus as the orbital, the plus minus the angular momentum operator, right? So remember chapter 5, we immediately gave us this raising or lowering this m state by 1 unit. So now that is G minus plus m. Let's go back to chapter 5, you remember? And states, because it's, so that is G and m plus minus 1, right? Then let's apply this numerical side, this drop. How to apply the drop? Here, since this is the joint eigenstate of J1 squared, J2 squared, J1Z, J2Z, not J. So we have to rewrite this one in terms of J1 plus minus J2 plus minus. Remember? So now, M1, M2. Okay, now. That is J plus minus, right? That is this part. And that is J1, J2, M1, M2, J1 plus minus plus J2 plus minus. Remember? Because this the J x components is equal to J1x plus J2x. Jy is J1y plus J2y, right? So the J plus minus equal to J1 plus minus plus J2 plus minus. Now we have this. So now let's do that. Since J1 only apply this in the subspace J1, M1, right? So you can leave here. Leave here. If you actually, I don't need this step. You just immediately in your mind that is only works on this, right? Because this independent of this plus here second one, J1, M1, and J2, M2, J2 plus minus. So this only apply this, right? When you meet this product of this in chapter 8, actually we'll deal with this type very often. So when you have this the eigenstate, the product of each individual, then your operator is also one of these subspace. You only apply that one, that correspond to eigenstate for that space. The others will not check, right? So this one, same thing like this, right? But this is replaced by J1. So H bar J1 here minus plus M1 J1 plus minus m1 plus 1. And here, this still keep, right, J1, J1, J2, and combine together because J1, and then the m1 plus minus 1, right? Raising over lowering. But m2 here, keep, right? Not change. So that is only for change is m1. Increase or decrease. And with this coefficient here. Okay, this term is J2 or m2, right? So that is J2 minus plus m2, J2 plus minus m2 plus 1. And then J1, J2, m1 keep, but the m2 raise or lowering by 1 unit. So I have two states here. That is because we have two operators. Okay. Now the left hand side, the right side equal, so we have the relation. That is, we are going to derive the first recurrent relation from this operator G plus minus sandwiched by these two states, right? So we have the recursion in the first. So relation 1 is squirrel, the first one, yeah. This one, right, equal to this one. So h bar cancelled. We have J minus plus m, J plus minus m plus 1 with states of J m. Sorry, J m, here. Wait. Yeah, here. This is not 1, right? This is J. This part equal to this part, right? Not equal to. Okay, we have two terms. J1 minus plus m1, J1 plus minus m1, and this case J1, J2, m1 minus. Yes, I made a mistake. Sorry, here. That's very important. So when this one applied to this is because J plus mass dagger equal to J minus 1. So this is actually, when you apply this dagger, right? So that is, I just made this one. So when you apply bra, this one here, this is instead of so m1 minus plus 1 and m2.
Are the negative signs inside of the parentheses the same? Or inside of the square root?
Yes, you're right. Just reverse. So now, you probably have this one. The other side is J1, J2, M1, M2, Jm plus minus 1. Because this one, right? So I have only applied this, but we have this before. And this equal to, and this one, the first is this multiply. Okay, this one. Here multiply this, right? That's the cat. So we have G1, G2, M1 minus plus 1, M2, Gn. Plus, so here, here this is plus minus, this minus plus. G2 plus minus M2, and G2 minus plus M2 plus 1. Gn, G2, M1, now M2, change. Looks like a little longer, but later when we apply, in some cases it can help us. So now this is I'm going to say equation 1. Time this out. Okay. And now this takes time. Yeah. We need to work on this. So Wednesday homework is okay, right?
Yeah.
Yeah. I think I already cleaned up, so can you just do Wednesday we are going to use this table and try to see how to apply the table. We know how to do that. That is our required as a graduate student. If undergraduate, maybe I do not need to spend too much time here. You try to give me the formula and try to use the table, but here we need to learn how to do it. This table is previous, once we have a G and M, then this is a column, and the row is M1, M2. Then you can find this crossover, that box gives us the Calabi-Scott's coefficient, but take square root. They give numbers, you have to take square root. Okay. All right.
Thank you.
Thank you.
Bro, I'm going
Okay, all right. All right, see you.
Bye.
Bye.
Nepal is not representing the language studies. There's an associate the language, other language. You should have got an Oh, okay. So we are like putting a table
I
tomorrow.
love how it's in.
It has
I wonder if it was like abroad and
I
then it
will
was
be
like,
able to complete it.
translated.
Yeah.
I'll get this is not done right, it'll be done right here.
Tomorrow 11, just come. Okay, you have a class or something around 11?
Tomorrow 11. I have lab.
Oh, 11. Yeah, oh, the 2 to 3. 2 to 4. Oh.
I know, yeah, he has got a lab. We gotta go there together.
Oh.
Jacob, he's gotta write on the board before my lab.
Oh. Hi, Jay.